So welcome back. So we just started chapter 4, which I had went over the vector space axioms with you all and given you a few examples of vector spaces and what maybe some of the benefit of thinking of vector spaces rather than just thinking of Rn can be. So definition: a vector space V, which I will abbreviate as VS for the remainder of this course so that I don't have to waste all the time writing vector space here, because a vector space is something that's going to show up a lot in what we do, so I don't want to have to constantly be saying vector or writing vector space out. So VS is what we will usually call these things. So a vector space V is a set of objects, a collection of things, right, called vectors. Again, these the reason why using quotes here is because they do not have to appear to be vectors in the usual sense, even though we will see that in every case they are, or they can be thought of as vectors in the sense that you have already thought of them. Okay, that is equipped with two operations. Okay, so these two operations are vector addition which we will call plus, and scalar multiplication. Okay, by scalars. The scalars for us will be real numbers. Now, this is not necessary. We do not have to pick these things to be real numbers. We could pick them to be complex numbers. Okay, so we could pick them to be imaginary numbers, and in that case, what we would be talking about would be complex vector spaces, so complex vector spaces rather than real vector spaces. So we're not even going to ever include this word, but this is technically the definition of a real vector space, because the scalars live in the real numbers. The scalars are in R. In fact, we don't have to think about the scalars being from either R or C. We are happy if the scalars are in what's called a field, but I won't say any more about that. So anyway, we have scalars. For us, our scalars are going to be in the reals. We have two operations, vector addition and scalar multiplication. And both of these satisfy the vector space axioms. So what are the vector space axioms? The vector space axioms is a list of properties that vector addition and scalar multiplication have that make them very, very similar. In fact, we'll see identical to how this works in the reals, or in Rn. Okay, so to remind you what the vector space axioms are, there's the list. Okay, so I went through these last time. I'm not going to go through them again, and I'm not going to write them out. It would take too long. But here's the list, so you can pause the video here if you want to, if you're referring to this later. But there's the list of vector space axioms. Okay. So it includes things like the existence of a zero vector, the existence of a vector additive inverse, okay, things like that. And we saw that there were some basic properties you're already familiar with how these things go. So some examples. Rn, right, for any n is an example. Okay, so Rn is your canonical example of a vector space. It has vector addition, it's got scalar multiplication, everything. It definitely satisfies the vector space axioms. Of course, we're cheating a little bit because those vector space axioms were dreamed up to mimic Rn in the first place. Here's another example. So let's let P sub n be the set of all polynomials up to degree n. Okay, so this is the set of all polynomials up to degree n. So what does that look like? So a naught plus a1t plus a sub 2t and so on all the way up to a sub n t to the n, such that all of the a sub i's are real, right? And of course t, the variable, is a real number. Okay. So this is the set of all polynomials of degree t all polynomials in t up to degree n is what this set is. This is a vector space. So what is vector addition here? So vector addition is pointwise sum of functions. And scalar multiplication what is that? That is multiplying a polynomial, right? Multiplying or scaling a polynomial by a real number. Okay. Yes, this should be t squared, sorry. Okay, so here our vector addition is pointwise sum of functions. Scalar multiplication is multiplying a polynomial by a real number. What this says is that using these two operations as my vector addition, scalar multiplication, this thing is a vector space. So remember that being a vector space, we get some extra things here. We get, for instance, the existence of a zero vector should be apparent here. So what is the zero vector in this space of all polynomials up to degree n? The zero vector is the polynomial, all of whose coefficients are zero, i.e. the constant zero polynomial, right? Okay, is the zero vector. What is the vector additive inverse, right? So if you have a polynomial, what is the vector you can add to it that makes it the zero vector? Well, it's just that same polynomial where you've replaced every single coefficient here with its negative, right? So that's how this works. Now, this shows what is the benefit of switching to language where we're not just talking about Rn constantly. Okay, now, to spoil the fun, we are going to see, as I mentioned last time, this is actually equivalent to some R to the big N. Okay, and again, you might be able to look at this and see exactly what R, to the big N this is equivalent to. But the idea here is that it allows us to apply the same sort of things that we were going to talk about for Rn to a setting that it doesn't look like, just by looking at it, it would actually apply to, but it's going to. So we're specifically going to see some examples that makes use of this when I talk about some things later in the chapter. Okay, but this is the first example that shows you, all this stuff that we were doing, right, that we thought maybe would only apply to Rn, applies to this setting as well. So I can use the sort of vector algebra that I was using in Rn, I can use that in this setting to say something. Okay. All right, so this is some motivation for why we should do this. Now, here's a definition. And this is the definition of a vector subspace. Okay, so a subspace, of a vector space V is a subset H of V that has three properties. Okay, so first property, the zero vector. So the zero vector of V is in H. Okay. Secondly, H is closed under vector addition. i.e., if if U and V are in H, then U plus V is in H. Okay. And lastly, H is closed under scalar multiplication. i.e., if U is in H and C is a scalar, so it's just something in R, then CU is in H. Okay. So what is this? So intuitively, what is this? What this is a subset of a vector space that is a vector space in its own right. Okay, this is a subset of a vector space that is a vector space in its own right. Okay. This definition, then what's the purpose of it, right? What's the purpose of this definition? This definition then allows us to check only these three things. Right? Well, what's the alternative, right? If I didn't have this definition, if I defined a subset of a vector space and I wanted to verify whether or not that was a vector space on its own, then using the definition of vector space, I would have to actually verify that it satisfied every single one of those vector space axioms, and there's a whole long list of those, right? This is better than having to check every vector space axiom. Right. In fact, this is saying that if it's a subset of a vector space, a thing we already know that is a vector space, we can basically use the fact that it's sitting inside a vector space to take care of having to check a lot of those vector space axioms. And so all we have to do is check that it contains a zero vector and it's closed under vector addition and scalar multiplication. That's it. So let's see some examples of subspaces. There's also going to be some confusing things I can ask about subspaces, but I think I will wait and actually we'll see. We'll see about that. I might go ahead and ask one. So here's an example. What is the simplest possible subspace of a vector space? So what is the simplest possible subspace of a vector space? What about the subspace that consists of only the zero vector? So the answer, the zero subspace. What is the zero subspace? H is the subset of the vector space that contains only the zero vector. Okay. Someone else said H is equal to V. That's a perfectly fine answer too, and I'll talk about that here in just a second. So in terms of simplest, in a sense, the subspace being equal to the entire vector space is also, an example of simplest. So I guess it really means, if you're talking simplest in terms of size or in terms of, ease of writing, then it depends. But anyway, so I'll talk about that in just a second. So what's the simplest possible subspace of vector space? So the zero subspace is an example. So the zero subspace is just the subset of a vector space that contains only the zero vector. So note very quickly, 0 is in H, so that's number 1 is checked. Number 2, what's the thing I have to check? I have to check that vector sum is closed, but the only vector in this subspace is the 0 vector. So the only thing I have to check is the single vector sum 0 plus 0, but that's 0. That is in H. We're good. And then the third thing I have to check, of course, is if I take any scalar c and I multiply it by 0, or the 0 vector, what do I get? I get the 0 vector, doesn't matter what c is, and that is in H for every c in the reals, so I'm good. All right, so this is definitely a subspace by that definition. Okay, so and another note, so fact, every vector space contains the 0 subspace, where the 0 subspace is the subspace consisting just of the 0 vector for that vector space. Okay, so a vector space at least has the 0 vector. Doesn't necessarily have more than that, right? But it at least has the 0 vector. Okay, so someone else brought up another example. If V is a vector space, then the subspace that is the entire ambient vector space V is a subspace of V. Okay? And so I don't have to check the 3 conditions are trivial to check because H is V and V satisfies all the vector space axioms. Okay, and so V satisfies all the vector space axioms, so does H. So it definitely satisfies that list of 3 abbreviated properties. Okay. All right, so this doesn't have a name. Just know that this is always a possibility. So when you think of a subspace for a vector space, the kind of extreme possibilities are that could be the 0 subspace consisting of a single vector, or it could be the subspace consisting of every vector in V. Okay, it could literally be V itself is considered a subspace of itself. Okay, all right. So here's an example. And I'm not going to check these properties. Or I'm not going to check these that it satisfies the properties. I'll just say it in words basically. Let P sub n be the so let's let this be the set of all polynomials with real coefficients. So we don't have to restrict its degree. We'll say of degree at most n. Okay. Okay. So then let's note that Um, so P sub n is a subset of the set of all real valued functions, for instance, defined on the reals. Okay. Let's call this set of all real valued functions defined on the reals, we're going to call that F. Okay. It turns out that F is a vector space. F is a vector space, and P sub n is a subspace of F. Okay, so I'm not going to check, but just quickly in words here, I have so first of all, the question is the zero vector of F present in is the zero vector of F present in P sub n? Does it belong to P sub n? And the answer is yeah, because the addition we're using here is pointwise addition of functions. So I'm looking for a function that when I add it to any other given function, it doesn't change that function at all. Well, that's the constant zero function. That constant zero function is included in the set of all polynomials with real coefficients degree at most n, because it's a degree zero polynomial. So 0 is in P sub n. The second thing is if I have two objects in P sub n, if I have two vectors in P sub n, that is two polynomials with degree at most n, when I add them together, do I get another polynomial of degree at most n? Absolutely. If I take any scalar c, so any real number c, and I multiply it by a polynomial of degree at most n, do I get another polynomial of degree at most n? Absolutely. So the three things are checked. And this is actually a subspace of this vector space F. Now, I'm not going to prove right now that F is actually a vector space, but you could check independently that it actually satisfies all the vector space axioms. Okay, so that's another example. Let's do more examples. Let's say, note, R2 is not a subspace of R3. Why? Well, R2 is not even a subset of R3. Right? That's what's required. First, it has to be a subset. Does the zero vector, so I got a question here, does the zero vector have different meanings in different vector spaces? Like, is there a vector space with different definitions, interpretations of addition, multiplication, so that the zero vector isn't just all zeros? Well, okay, so the first question is kind of sort of, so the answer to your first question is yes. Are there different meanings to the zero vector? There's different meanings in the sense that, so for instance, in the examples we saw, the zero vector for one of those things was the vector of all zeros, so say in R3. But in one of these examples where we are looking at, say, the vector space of polynomials, degree at most n, then that object, right, is the zero function. It's the zero polynomial. Now, of course, yes, that polynomial can be listed as a bunch of zeros, but we could even be talking about a more general case where we have the vector space of real valued functions, in which case the zero vector would still be the zero function. Now, does the zero vector depend on your definition of vector addition and scalar multiplication? Yes, it does. It does, and so in different settings, it can be slightly different. And so, can you the zero vector is the additive identity? Yes, that's exactly what it is. So why is R2 not a subspace of R3? It's not a subset of R3, right? Because in R2, what is R2? R2 is the set of all vectors xy such that x and y are real numbers, right? It's the set of all ordered pairs. Well, what's R3? It's the set of all vectors x, y, z such that x, y, and z are real numbers. So, for instance, 0, 0 is in R2, but 0, 0 is not in R3, right? So R2 is not a subset of R3. So it's not even a subset of R3. Okay, which is one of the first things, if I go back to my definition of subspace. So my definition of subspace, a subspace of a vector space V is a subset of V. Okay, so this is not even a subset. Now, you are not wrong to think that intuitively R2 should be a subspace of R3. So here's where that complicated thing that I mentioned comes in. Okay, so define H to be the subset of R3 that is ST0. So this is defined such that S and T are in the reals. Okay. Right, so someone brought up in the chat that you could look at XY0. But see, XY0 has 3 slots, right? But R2 doesn't have 3 slots, it has 2 slots. Right? So, I mean, R2 is the set of vectors in with 2 slots, right? Not 3 slots. So XY0 is in R3, but it's not in R2, right? So here's how we remedy this seeming issue with our intuition. So define H to be the set of all vectors ST0 or S and T are real numbers. Okay, this is a subset of R3 and is a subspace of R3. Okay, so let's check, right? So someone said, wouldn't XY0 get you a vector space that is effectively equivalent? I like that word, that combination of words. Effectively equivalent to R2, yes, but we're going to have another word for that. Okay, so that's exactly what I'm talking about now. So I've defined a subset of R3 that is the collection of all vectors that are just any real numbers in the first 2 slots with 0 in the last slot. Okay, so this is a subspace of R3. To see that, so the first thing I have to check is the 0 vector in H. Yes, right? The 0 vector is in H because 0, 0, 0 is a vector such that 0 and 0 are in R, right? So it's definitely in H. Okay, and so the second thing, let's let U and V be in H. Okay, is U plus V in H? So let's check here. So if U and V are in H, what would they look like? They would look like U1, U2, 0. And added to that, I would have V1, V2, 0. That's what they would look like if they belong to H. When I add those together, what do I get? I get U1 plus V1, U2 plus V2, 0, which is definitely an H. Okay, and then the third thing I have to check is C times U in H for all C and R. Okay, well, the answer to that is C times, say, U1, U2, 0 is C U1, C, U2, 0. So that's real number, 0. That is in H. Okay. So it's a subspace of R3. Okay. Yes. So someone said the word isomorphic, right? So absolutely, that is exactly where we're headed with this. But I won't use that terminology officially till later. But so what we have seen here, thus, we have found a subspace of R3 that is equivalent to R2. But notice, it is not equal to R2, but is not equal to R2. Right? It's not equal to R2 because R2 only contains vectors with 2 entries. Okay, this will be tidied up later. So R2 is isomorphic to H. Okay, I'm not going to define it yet, but what isomorphic means is that as far as vector spaces go, they are equivalent. So anything you are doing that is only doing vector algebra with R2 and with H is going to be exactly the same. So any linear algebra done in H is exactly the same linear algebra done in R2. That's what isomorphic is going to mean. Okay, so this is a very important point. Okay, so let's do another example. So maybe I should mention one more thing before I move on to the next little bit and then the next section. So these 3 things are all needed. I can't undo any of these. If I undo any of these, then what I get is not a subspace in the way that I want it to be. So, for instance, you have to check these independently. So there are examples of subspaces that satisfy one and not the other 2 for all of these things. Okay. In fact, you will see that on your exam. So, which is next Friday, by the way. I didn't make the announcement yet, but I'll do that later today. Your exam is next Friday. So I will give it to you next Friday, and it'll be due the Monday after that. Okay. So let's continue here. So definition, given a set of vectors, say V1 to VP in a vector space V, the linear combination, or I shouldn't say the linear combination, I should say a linear combination. So a linear combination of those is exactly what it was before, C1 V1 plus C2 V2, and so on, all the way up to CP VP, where the CI's are all real numbers, all scalars. Okay, and span, so this is linear combination is what we're defining here, and the span of the set of vectors is the set of all such linear combinations. Okay. So this defines linear combination and span in the more sorry, I don't mean this Friday. The 9th is this Friday. It would be next week, not this weekend. Okay, so so this is the set of all linear combinations. So now I've defined that for a vector space. So then here's the theorem. If V1 through VP are vectors in a vector space V, then the span of V1 to Vp is a subspace of V. So you have a list of vectors in a vector space V. The span of those vectors is a subspace of V. Okay, and so here's some terminology here. You can check this on your own. Okay, this is a good thing to check on your own. Notation or terminology, really, not notation. We call H, which is the span of a list of vectors, the subspace of V, the subspace spanned by the vectors V1 to Vp. Sometimes you'll hear that referred to as the subspace generated by a list of vectors, and we call that list of vectors V1 to Vp the spanning set of H. Okay. And yes, the exam will include chapter 4 stuff. Okay. All right. So here's a couple of things to have you consider. This sort of approach is going to allow us to revisit some of those earlier problems that we did in chapter 1 from a new angle. We're going to see it in a new light. But before we can talk about those things, we have to define some more quantities. And so here's first quantity is the notion of the null space of a matrix. Okay, so the notion of the null space of a matrix. Okay, so definition is the null space, and we can define the null space for a rectangular matrix. So the null space of an M by N matrix A is, so this is written as null A. That's how we write the null space. So the null space of an M by M matrix A is the set of all solutions to the homogeneous equation AX equals 0. All right. i.e., in set notation, the null space of A is defined to be the set of all vectors x in Rn such that Ax is equal to the 0 vector. Okay. So here's some facts about the null space. So before I've even computed anything here with the null space, here's the following theorem. The null space, there's a reason why we use the term space here. So the null, I don't know why I capitalized this, the null space of an M by N matrix A is a subspace of, well, it's a subset of Rn, right? A is an m by n matrix. I'm multiplying on the left by A. The x's here need to be of size n, right? They have to be an Rn. And so this is a subspace of Rn. So the definition says it's a subset of Rn. It's actually a subspace of Rn. This is not too hard to check. Maybe I'll check it here in a second. Equivalently, the set of all solutions. So this is the nicer way of saying what I'm about to write out in words. So the set of all solutions to AX equals 0 is a subspace of Rn. That is it's m homogeneous linear equations and n unknowns, right? So that solution set is a subspace of Rn. Okay. Just to quickly check this, does 0 belong to null A? Right. So let's prove this quickly. Is the 0 vector in the null space of A? Well, A times 0 is equal to 0, so yes, it is, right? i.e. 0 vectors in null A. Okay. All right, so so that's to check 1. To check 2, let U and V be in null A. Then what that means is that AU is equal to the 0 vector and AV is equal to the 0 vector. But then AU plus AV is equal to the 0 vector. But this implies that A times U plus V is equal to the 0 vector. But what does this imply? This implies that U plus V is in the null space, which was what I needed to check. This is just from those basic matrix properties, right? And the third thing I need to check, if U is in null A, then AU is equal to the 0 vector. Note C times AU is equal to the 0 vector. It doesn't matter what C is. But then that means that A times CU is equal to the 0 vector, because I can pull scalars through matrix multiplication. And so CU is in null A, which is the last thing I have to check. That's it. Okay, so that's the proof. Okay. Now, the reason I did this proof is to illustrate a fundamental fact. And I'm going to be beating you over the head with this because this is a nice characterization of the null space. Note, it is very easy to check if a given vector is in the null space of A. Right? What do I do? Just look at AX, we'll say a given vector X, and see if it is the 0 vector. Right? So checking whether or not a vector is in the null space is really easy. You just multiply it by A and see whether or not that's a 0 vector. Right? Okay. Someone was saying, what's the difference between subspace and subset? A subset is not saying anything about the later structure. A subset of a set is literally just a set, all of whose members, all of whose objects are also in some larger set. Okay. So the set of all even numbers versus the subset of even numbers just containing the numbers 2, 4, and 6, right? So as someone pointed out, with subset, it could literally be any sub-collection of objects, whereas subspace has some additional requirements that have to do with the vector space structure. Okay. All right. And so that is one thing. It's easy to check if a given vector is in the null space. But how do I... So that's just to check if a vector is in the null space. But how do I explicitly describe the null space of A? Okay. How do I explicitly describe null A? Here is where that, you remember when we did parametric vector form back in chapter 1, here is where that's going to come in real handy for you. So example, what do I mean by explicitly describe here? What do I mean by this? What I mean by this is I want to find a spanning set for the null space. So find a spanning set for the null space of the matrix A, which is the 3 by 5 matrix. I'm going to read row-wise: -3, 6, -1, 1, -7. The next row is 1, -2, 2, 3, -1. And the last row is 2, -4, 5, 8, -4. Okay. All right, so there's my matrix A. So what's the first step to this? Find a spanning set for the null space. The null space of the matrix, of course, is the set of all vectors that satisfy the equation AX equals the 0 vector. So then what does it make sense to do? It makes sense to look at this equation. So let's look at the equation AX equals 0. So if we form that equation, or rather, let's form the augmented matrix A0 and then reduce it. Okay, so what does this reduce to? So if I form the augmented matrix A0, I'm not going to recopy that. You can use your imagination. Take A here and write 3 zeros, right, in the last column. If I reduce that, it is row equivalent to what matrix? Well, it's row equivalent to the matrix 1, -2, 0, -1, 3, 0. In the next line, I get 0, 0, 1, 2, -2, 0. And in the last line, I have nothing but zeros. Okay. What does this correspond to as a system? So as a system, this corresponds to x sub 1 minus 2, x sub 2, minus x sub 4, plus 3, x sub 5 is equal to 0. And then the second equation I get is x sub 3 plus 2, x sub 4, minus 2, x sub 5 is equal to 0. And then the last, of course, is 0 equals 0. That's not going to give me anything. So now I want to use the fact that I understand free variables and how to write this using parametric vector form. So use parametric vector form. I want to use parametric vector form to solve for the basic variables in terms of the free variables. So how did I do that? How did I come up with the second matrix? I did row operations, except I did them mentally. I did them mentally and quickly. So at this point, that's from now on, when we do row operations, they're going to be done like that. It's going to be assumed that you can do the row operations to get that job done. Okay, so I've reduced it to this linear system. So I want to solve this linear system for the general solution. So find general solution. Okay, well, I can do that pretty quickly. So I can solve x sub 1 and x sub 3 for free variables x sub 2, x sub 4, and x sub 5. So here, maybe I'll write this here. Here's my, there we go, there's my system I'm solving. So when I write that solution out, I have x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5 here. This is my general solution. So writing out my general solution, then x sub 1, I can solve that in terms of x sub 2, x sub 3, and x sub 4. What is that? Well, I get 2x sub 2 plus x sub 4 minus 3x sub 5. Right? That's what goes in the first slot. X sub 2 is free, so x sub 2 is just equal to x sub 2. X sub 3 I can solve for in terms of x sub 4 and x sub 5 here, so this is minus 2 x sub 4 plus 2 x sub 5. X sub 4 and x sub 5 are free. So there's x sub 4 and x sub 5. No, it doesn't mean you can use MATLAB on the homework. You still got to do it by hand. So continuing on here, what do? I want to use parametric vector form and actually write this out as vectors weighted by the free variables. So what do I get here multiplying x sub 2? I get 2, 1, 0, 0, 0. Plus x sub 4 times 1, 0, minus 2, 1, 0. And then lastly, plus x sub 5 times minus 3, 0, 2, 0, 1. There we go. Okay. All right. So I get any general solution as a linear combination of these three vectors where these are the weights. What does this say? Now, what does this statement that I've written here say? Well, this statement says literally that the null space of A is equal to the span of the three vectors. If I've called this, I'll call this vector u, this vector v, and this vector w. It says that it's the span of u, v, and w. And so I have found exactly my set of vectors that is the spanning set for A. So what am I saying when I write this? I'm saying that any thing that is in the null space, that is any solution to the equation ax equals 0, has to be of this form. This comes from chapter 1 stuff, right? So it has to be in this form, okay? But in this form means it has to be a linear combination of these three vectors, where which linear combination it is means a choice of these weights, which is a choice of the free variables here. So it's got to be a linear combination of these three vectors. What that's saying is that any thing in the null space is a linear combination of these three vectors, so it's in the span. Vice versa, the span contains every vector that's in the null space. So span contains everything that's in the null space contains everything that's in the span, and these things are equal. These two things are equal. And so we found our explicit description of the null space. Okay, so I went a couple minutes over. Now, a couple things that were mentioned. Yeah. Well, you can still use MATLAB to check, that you've got the right thing. Obviously you can use MATLAB to check your answers, but in terms of doing the homework, you should write out all of those row reductions, right? Because for some of the problems, of course, like using row operations to make your life easier when computing determinants, you actually need to keep track of them anyway. Okay, so that's that. So we have talked about the null space. In the description of this video, I added in the column space, but I'll move that over to the next. I'll move that over to the next video. So on Friday, we will finish talking about the column space, and then we'll talk about bases and linear independence and things like that. Do we have MATLAB homework? Not yet. You will have MATLAB homework basically after you turn in your first. After you turn in your first exam, you will have your first MATLAB homework. Okay. The submission for the homework is not up. Someone else emailed me about that. I'll do that later. So this afternoon I'll add that so that you can upload it then. So yeah, submission's not up yet. Okay. So I think that's it. I think that's all of the homework that's all the questions I'm seeing. So anyway, okay. Will there be practice exam problems? No, since it's going to be an online exam, open note and everything, and you have a couple days to do it. The exam itself are the practice problems. Anyway, so that's that. I will see you all on Friday. So I'll let you know about actually, and I may give you an extension on the homework that's due on. I think your next homework's due Friday. Maybe I'll make it due Monday or something instead. Anyway, I'll see you all on Friday.